Hi everybody, and welcome to a discussion with Michael Lubasch, where we will discuss his paper, Classically Optimized Hamiltonian Simulation. You can find the paper in the description, and I hope you enjoy our discussion. I think we can start talking about Hamiltonian simulation as a starting point for the paper. If you wouldn't mind introducing a little bit what that is to begin with, and then also why this is an active field of investigation.
Yes, of course. So the topic of Hamiltonian simulation is basically it's about simulating the time evolution according to a Schrödinger equation with some specific Hermitian operator that represents the Hamiltonian. And the reason why people are looking into this is because it's known for quite a while that for quantum many-body systems, so for the quantum many-body Schrödinger equation, quantum computers are simply efficient in the number of quantum particles in realizing Hamiltonian simulation. So at the same time, classical methods struggle significantly with simulating many quantum particles. So it's one of these topics where we expect to see a quantum advantage using quantum computers. So where we expect to see quantum computers outperform classical computers sooner. Yeah.
Okay. I think one interesting point, so the other part of the title essentially is this classically optimized part. So we are looking to do Hamiltonian simulations, and as you outlined, there's a good chance that we could have quantum advantage if we do that on a quantum computer. It's very interesting that we're then trying to also leverage classical computational devices in optimizing these simulation capabilities. Would you mind elaborating a little bit on where that idea comes from? It seems to me that if we're looking to do Hamiltonian simulation and we're looking to apply that on a quantum computer, that the natural thing to do would be to have sort of a quantum algorithm end to end for this. What is the reason for trying to optimize the circuits in a classical computer?
So the reason is that so the classical optimization allows us to make better use of the hardware that we have. So one way of thinking of it is as a compilation step. So similar to what a classical compiler does. When you tell the compiler to optimize your code while compiling, our goal with this project was to basically optimize circuits classically, so using a classical computer to optimize quantum circuits, well, simply to make better use of quantum hardware. So the situation is that there are several existing ideas to realize Hamiltonian simulation with quantum computers. Perhaps the most widely used one is based on Trotter product formulas. So that's a very nice idea. Also because for quantum many-body Hamiltonians, in second quantization, it immediately leads to unitary gates that one can run on a quantum computer. The problem with Trotter product formulas is well, they can lead to deep circuits. So if we have noisy gates, as we currently have in our current devices, and we want to simulate for long times, so if our goal is really to do Hamiltonian simulation for really long times, well, then these Trotter product formulas, they can lead to really deep circuits. So what we looked at in this paper is whether we can start the circuits from these Trotter product formulas and then use classical techniques. And in our case, we use tensor network algorithms to compress these circuits into much shallower form, right? Such that with the same gate count, so using the same number of gates, we can go to much longer times than using Trotter product formulas.
Okay. Why would you start? So if you have a setup like that, why would you start with a trotterized set of gates to begin with? Why not try to approach the problem from a completely fresh perspective with the classical optimization?
So that's actually what we did. So it's a very good point. So we used the Trotter formulas to compare with. So that's why I mentioned them.
Okay. Mm-hmm.
So yeah, basically that's how it was.
Okay, so there's no two-step process where you would first perform a trotterization and get a set of get a quantum circuit or a set of gates, and then after that feed that into a new algorithm that tries to compress it. It's not a two-step process in that way. It's rather a one-step process when you're doing this in the classical setup.
It does not need to be a two-step process, but you can. So our approach can be done in this two-step way. And the motivation, actually, there is a good motivation for doing it in that two-step way, which is that you can compare to Trotter, you know? So doing it in the two-step way gives you an architecture, so it defines your circuit, and it gives you a baseline, the Trotter baseline that many people are familiar with. And now you run this algorithm that we've developed, and you will improve, right? The results will be at least as good as Trotter, but you can improve upon them.
Okay, but the algorithm that you've developed doesn't rely on the input being trotterized to begin with. You could as well apply that to a fresh set of to a fresh circuit, let's say, and then optimize that by itself without having done the first step.
That's right. Yeah.
Okay, then I see. Yeah, very good. So can we then talk a little bit about how this algorithm works, or kind of what the objective is when we're saying that we're looking to optimize this? You mentioned that we tend to get deep circuits with trotterization, and that we might want to make them to compress them in that sense. Is that the core? Yeah, right. Is that the core objective of this algorithm that was developed, or is the goal of the algorithm, so to speak, something different?
So the main goal of the algorithm is to reduce the circuit depths required for long Hamiltonian simulation. Now, to achieve this, we're utilizing a specific set of tools, these tensor network algorithms, and they have certain requirements. And the requirements are, in our case, the geometric locality of the Hamiltonian. So what's important for our methods is actually that we have geometrically local interactions in the Hamiltonian. So that's one thing that we're using. Yeah.
Okay. But maybe we can look at the objective function here quickly. So I think the cost function or / objective function of your algorithm is this, correct?
Right.
Would you mind giving some conceptual understanding for what we're trying to do with this? What is this what information does this function encode?
This function is encoding the operator distance. So so the idea is to minimize the distance iteratively. So in such a way that so very similar to how neural networks are trained. Here we're training a quantum circuit. And the goal of the training is that the quantum circuit faithfully represents the Hamiltonian simulation that we wanted to represent. Yeah. To achieve this, we effectively time evolve the quantum circuit in small time steps. And in each time step, we're just minimizing this Frobenius distance between the quantum circuit that we're optimizing and the time-evolved circuit, time-evolved from the previous time step. And if one writes out the squared Frobenius distance for these operators, one realizes that the resulting term is this equation 1 that one has to maximize to minimize this operator distance in each time step. Yeah.
Okay. And maybe we can talk a little bit more about the time steps here. So we're trying to time evolve this system over some longer time period, and we're effectively doing that by splitting up the time period, if I understand correctly, into smaller sub-intervals. Are we applying a set of gates for each time step, or are we looking to compress to evaluate the final result of this with one evaluation? If you see the difference, what I'm trying to say, like what does it actually mean that we're splitting this?
Right. So several time steps go into one circuit. So that's crucial. So if you have a Trotter formula, a traditional Trotter formula, you'll have one circuit per time step. So if you have 2 time steps, you have twice the circuit depth. 3 time steps, 3 times the circuit depth. So what we are doing is different. We train a circuit to describe several time steps. Yeah. That's why we call it compression, right? So another word we use for these techniques is quantum circuit compression, because effectively, if we do 3, 4, 5 time steps, we all compress this into a single circuit, right? That's what these techniques do.
Okay.
And then
is that then reflected in the? Sorry, go ahead.
So the idea is that we summarize several time steps into a chunk. So let's say we would have 50 time steps per one circuit. Then we can still append these circuits. So one important aspect of this work here is that it's actually all classical. So now the question is, where's the quantum advantage, right? So the quantum advantage actually comes from appending these circuits on a quantum computer after the individual circuits were optimized on a classical computer. So running them in their appended form is actually classically hard. Yeah.
Okay.
And one aspect that might also help here to understand the situation is that if you append the circuits, the total time grows linearly with how often you append them. So basically that is how one can easily understand like where the quantum advantage might or might not come from. Yeah.
Okay, understood. And then the formalism that we use for this, we're saying that we're splitting this up into S time steps, I believe it is. Yeah, exactly. And the reason for doing that goes back to the point we said in the beginning, that we're conceptually at least starting with a trotterized circuit that then has S different gates that we would apply in sequence, and then we're using that as our starting point to conceptually say that we're splitting the interval up into S different time steps, but then in reality, in the compressed circuit, we're not really taking S time steps, we're taking some smaller amount of time steps. So we're, again, merging those shorter time intervals together into something larger so that every gate that we ultimately apply covers more than tau time, like tau length worth of time evolution. Okay.
That's right. So the S time steps, they're all compressed into one circuit, right? So with Trotter, they would be S circuits, but in our case, we compress them into one circuit.
Necessarily one, or could there be some larger amount? Like, is the compression always back to one circuit rather than S, or is it just some smaller number?
So in our case, I mean, if we would say we have 2 circuits, right, or 3 circuits, we would simply call it the circuit depth, right? So in our case, we define we always speak of one circuit, but that circuit has a parameter, right, which determines its expressivity and also it's how hard it is to optimize classically, which is the circuit depth. So so if you like, you could say, you optimize 2 or 3 circuits, but in our case, we simply say that the circuit that we optimize, the single circuit we optimize, has a circuit depth, and that circuit depth is the variable that we also study, right? Like how things improve as we increase the circuit depth.
Yes. Okay. It's a better word to use for it. Let's stick to circuit depth. So we're saying that we have one circuit in the trotterized case with a circuit depth S, and we're compressing that circuit depth in the second algorithm that you've now developed into something smaller. That's my understanding right now. Please correct me if I'm wrong with that. And my question is then whether the circuit depth of this new circuit is always 1, or if it's generally some larger number.
No. It can be any number, as long as the circuit depth can be optimized classically. So, so the problem is, in general, classically optimizing deep circuits is exponentially hard in the circuit depth for sufficiently large systems. So it's extremely time consuming optimizing deep circuits. And so, simply speaking, if I go from circuit depth 1 to circuit depth 2, the classical cost, it runs 2 times longer. So now if I go from circuit depth 2 to 3, it again runs 2 times longer. Now it's already 4 times longer than initially, right? So there's this exponential growth of the classical cost in terms of circuit depth, with regards to circuit depth. So classically, we can't go to circuit depth, let's say 10 or 11 easily, with these methods. But what we can do is we can work with circuit depths up to there, let's say up to circuit depth 10, and compress a lot into these circuits. And that's really the power of this approach.
Okay, understood. Very good. So then let's talk about the actual optimization that you're conducting. So in optimizing, I think there are 2 steps that you take. So I think it's tensor network contraction and then also gate optimization that are the 2 steps of the procedure. Would you mind elaborating a little bit on both of those and to paint a picture of what the algorithm is doing?
Yes. So the cost function in equation 1 is a product of basically these 3 operators there, and then this TR denotes a trace. And then this RE denotes the real part. So what we're calculating there is the product of 3 operators. And then we're calculating the trace and calculating the real part of this thing. And this cost function we want to maximize. So it depends on this parameter theta. Theta are the gate angles in our circuit. So now the question is, how do we optimize this cost function using these gate angles, right? And so what we've investigated in this paper is several different optimizers to optimize these angles, but to calculate the cost function for each choice of angles, and also calculate gradients and Hessian, right? The Hessian matrix for this cost function. We perform tensor network contractions. So it's it turns out that if the circuit is shallow and 1D, but in 2D it would work similarly. Well, let's stick to 1D. So if the circuit is shallow and 1D, we can calculate, and the Hamiltonian is geometrically local in 1D. We can calculate this cost function using tensor network techniques for hundreds of qubits efficiently. And we can also calculate gradients and Hessian, the Hessian classically efficiently using tensor network techniques. And then the question is still, like, if we can calculate the gradient, if we can calculate the Hessian and the cost function itself, which optimizer performs best? And that is what we studied in the paper. So we compared a coordinate descent-like optimizer that finds the optimal angle one after another to a global Hessian approach that is very costly in each step, but very accurate. I think the method that performed best in our case was an LBFGS approach that uses an approximate Hessian at each stage and is very fast. Turned out to be really fast. For the that was the optimizer. Yeah.
Before going into the comparison between the optimizers, could we linger a little bit more on the tensor network contraction? Could you maybe give a little bit more detail on how we're conceptually evaluating, for example, the Hessian matrix using those techniques? What is it that we're able to leverage with this tensor framework to extract those quantities from the circuit that we have?
So basically what we're doing is we're calculating this quantity 1. So this equation 1, if you think of 100 qubits, let's say we assume we have a circuit that acts on 100 qubits, well, then these operators U dagger, x both minus I tau h and US minus 1, each one of them is a 2 to the power 100 times 2 to the power 100 matrix. So, but the thing is, they have structure. And that structure we can use. And the structure they have in our paper, which is crucial for these methods to work, is this U object is a shallow circuit. This Hamiltonian considered here is geometrically local in 1D. And US minus 1 is a shallow circuit. And shallow means it's constant depth, but we actually mean more. We mean that it's a low depth. Let's say 2, 3, 4, 5 layers of 2 qubit gates. So in that case, if you look at the circuit, basically one can look at this expression in 1 in terms of tensor networks. One can write it in terms of tensors. Then the gates, these 2 qubit gates that we're using in our ansatz, they simply become tensors in this picture, and it becomes a graph of tensors, and that graph will be very long, like very wide because of the 100 qubits, but it will be very thin. And this thinness is something we can make use of by using tensor network contractions. So
are you referring to the figure that we have, this figure 9 here? Is that maybe? Yeah. Okay.
Right.
You're saying that we can transfer the circuits into a tensor formulation akin to what we see, let's say, at the top here, and then that helps us in the compression. That's my understanding right now. Would you mind explaining, with the help of this figure then as well, first of all, maybe why we can transfer this to a tensor notation and why that conceptually helps us compress some of these systems, and then also, stepping through the different steps in this figure.
So ultimately, the reason why we can transform equation 1 into this tensor notation is simply because equation 1 is built from gates, from unitary gates. And these unitary gates in equation 1, in our paper, they're all 2 qubit gates or few qubit gates for these geometrically local Hamiltonians. So these few qubit gates, they are just 4x4 matrices, or also geometrically local 4x4 matrices, or depending on the Hamiltonian, right? There might be 8x8 matrices, but they're small objects. So now in the tensor picture, we just call them tensors. right? So a 4x4 matrix, it's a tensor with two indices where each index takes on 4 values. But it's even easier to think of tensors looking at the corresponding quantum circuits, because then each leg has dimension 2, right? Because we're considering qubits, and then a 4x4 matrix would be a tensor with two indices going in and two indices coming out, right? So because we have these linear operations, these few qubit gates that build our circuit and are required in our cost function 1, we can simply call them tensors, right? They're just generalizations of vectors and matrices. So now if we write out the tensor, if we draw this diagram of tensors that corresponds to this equation 1, we'll find that it consists of 3 parts. The first part is u dagger of theta, which is our ansatz at this point. The middle part is e to the minus I tau h at this current time slice, right? And the last part is us minus 1, which is the circuit from the previous time step. And these 3 parts, if one looks at them in the tensor picture, they just look like a very, very wide but very thin structure as a graph, right? And so what we do is we represent them by matrix product operators, simply because that's something that we can use here in this formalism. And these 3 matrix product operators, they're drawn here. So these 3 very thin, very wide but thin parts, they're now represented by these matrix product operators. And these matrix product operators have this pictorial representation that one can see in this figure 9. And then taking the product of them is precisely what's shown here in this figure 9, and taking the trace, right? So what this figure 9 represents is essentially the tensor network representation of the cost function in equation 1. Yeah.
Okay, so if I'm reading this correctly, you start from the top here, and then it's compressed as you go down in the figure. And you're saying that each step here corresponds to a product, and then consequently or subsequently a trace evaluation.
That's it. It's just a matrix vector product. Yeah. It's like a 1D. It's like a one-dimensional partition function. So, yeah. So it's just a simple vector matrix product until you end up with a scalar in the end. Yeah.
Okay, and then this compression, this network contraction, helps us evaluate, for example, the Hessian that we were discussing before. The end result of this contraction would somehow be those quantities that we are interested in. Or how do we bridge the gap? So fine, we have this figure now where we can compress the original input that we had. How does that actually help us in the original question we had of evaluating for example, the Hessian?
So this network here, after calculating it, spits out one number, just a complex number, and that number can be a gradient value of one parameter, or it can be a Hessian matrix element for one pair of parameters, or it can be the cost function itself. So all of these quantities, they have the same form as this figure 9 shows.
Okay, understood. And then with the help of this, then we can also apply the optimization that we were discussing before, the different versions of optimizers that we have, and that in combination then allows us to evaluate the results that we have in the figures.
Right.
So, okay. Maybe then we can start having a look at some of the figures and then discuss what different evaluations were actually compared. So if we start with figure 1 that we have on the first page here, would you mind describing what we can see in these 3 subfigures?
Yes, of course. So So first of all, what's shown here is the error of the optimized circuit or a trotter circuit with respect to the exact time evolution circuit. So we're looking at small systems here where we can actually compute the exact Hamiltonian simulation classically, which is possible for small systems. And now what we're comparing is in these three different panels, in these three different rows, we're comparing the performance of the classically optimized circuits for three different circuit depths. So, so in the top panel, we optimize a circuit of depth 1. In the middle panel, we have a circuit of depth 2. And in the last panel, we have a circuit of depth 3. So as you increase the circuit depth, the answers, just like a neural network, becomes more expressive, and it can do more things, right? So it becomes more interesting, but it also becomes harder to optimize classically. So what you can see here, maybe I first explain the baseline comparison, the trotter results. So the so the dotted pink curve is a first order trotter formula. The dashed purple curve is a second order trotter formula, trotter 2. And then the last panel also has a solid pink curve, which is a fourth order trotter formula. So the order just tells you how accurate they are, but also but it also tells you, so as higher, so as the order of the trotter formula gets higher, also the circuit to represent it has to be deeper. And what we are comparing here is in each panel, the trotter circuits have the same circuit depth as our classically optimized ones. So trotter 1 and trotter 2 can be represented for this particular Hamiltonian we studied, can be represented with depth 1. Yeah. But we can also embed trotter 1 and trotter 2 in depth 2. But then in depth 3, we can also embed a trotter 4. Yeah. And what we're comparing to is our classically optimized results with different numbers of time slices. So this S is the number of time steps we're using to optimize the quantum circuit. So ultimately, we want this S to be really large, like infinitely large, because so when we optimize, we actually make an approximation that depends on S, and that approximation gets better as S increases. So ideally, we want to have this S as large as possible, and so what we can see here is that there are also these results that we call exact, which correspond to this scenario of infinitely large S, right? That is basically the best we can do with the circuit. There's nothing. That's basically the limit of the expressivity of the circuit. And so using a finite S, which is required, right, for this whole calculation to be efficient, we have a certain region in time where we are actually diverting from the best possible result, right? This yellow curve. But what you can see, what the key result here is that we always hit this yellow curve, right? So the classically optimized circuits at a certain value of time, they always follow this yellow curve eventually, which is representing really the expressivity of the circuit. And this yellow curve is significantly better than the trotter results. So this is an error, right? So smaller is better. And so the yellow curve here, it's 2 or 3 orders of magnitude below the trotter results. And that's really the selling point of our approach, right? That it can decrease errors orders of magnitude below the Trotter error.
Okay, maybe a couple of follow-up questions when it comes to the problem formulation as such. So we're evaluating something here, and specifically, I think the Hamiltonian that's associated with this is the one reported down here. Would you mind, first of all, explaining what kind of problem we're looking at here? So we have this Hamiltonian here associated with these figures, and somehow we're receiving also an error here with the so-called exact solution. Why is it that we have an error in this exact solution to begin with?
Because it's so that's simply because of the expressivity of the circuit. So what we call exact here is, given a circuit of depth 1, you consider S being infinite. What is the best you can do with this circuit? Yeah. So exact is slightly misleading, I guess, right? But well, that's how it is. Yeah.
Okay. So by exact, if I paraphrase then to make sure I got it correctly, is the best you can do with that depth of circuit. Regardless of what circuit you pick, so long as you restrict it in the depth, this is as good as it's going to get for that particular evaluation.
Right.
Okay. Why is it increasing with time? So, could we talk a little bit about the time axis here as well? So we have some time evaluation. What does that actually represent in this case?
So the error grows with time because the circuit depth is fixed. So in each panel, the circuit depth is fixed. Let's just focus on the third panel, right? So we have a certain circuit, it's of depth 3. And what we're trying to do now is we're trying to train this circuit to represent Hamiltonian simulation for several different moments in time, right? So this time axis goes from 10 to the minus 2 to 2, right? Or slightly larger than 2. So we're taking the same circuit and we're trying to address the question. So if I use that circuit to represent Hamiltonian simulation of time 10 to the minus 2, what's the error I get, right? Compared to the exact Hamiltonian simulation. But we're also addressing the question, I take the same circuit, I train it to represent Hamiltonian simulation up to time 2, right? Let's say specifically for time 2. What error do I get? The same circuit depth to represent time evolution up to time 2. So the intuition why this error has to grow is because because we strongly believe that that the complexity, the circuit depth of Hamiltonian simulation for such models as considered here, it has to grow linearly with time. So if we fix the error, if we say, how does the circuit depth has to grow in time for fixed error? Well, then the best result we know of is that the circuit has to grow at least linearly with time. But if you fix the circuit depth, right? So, well, then your error has to grow, right, as you increase the time. Yeah. Right.
My follow-up question that I'm really interested in, and really why I started to talk about time, is if we look at the different lines that are plotted here, if we, for example, take the either of these S curves, if we look at the slope of these, it seems like we're sort of increasing linearly at a certain, or maybe not linearly, but linearly in a log scale at least here. And then we're catching up with the exact solution, at which point the error starts to rapidly expand or rapidly increase as a function of time. What is the reason for this kink that we see here? So fine, they're catching up to the exact solution, but it looks like the exact solution is sort of that it keeps the same quantitative evolution through time, let's say, but whereas we have a very distinct two-region setup for these different curves. Do you have a conceptual explanation for why that is?
So the reason is a bit technical, I guess. Not sure it's so interesting, but it's important to emphasize and explain. So we are actually using a first-order Taylor approximation of the time evolution operator in our optimization. So so this blue line here represents this Taylor error that we're using in the optimization. So that should, I think it should grow linearly, right? As you pointed out, or quadratically. I don't know. I would have to think about it. But the first region that you see here is this Taylor error. It's fully due to how we optimize the circuits in each time step. And what we're doing there is really using a Taylor approximation of lowest order. The second region is this region where the optimizer hits the limits of the expressivity of the ansatz. So the first region, we see the limitations of the Taylor approximation. The second region is where we see the limitations of the ansatz, and they have this kink, right? And the kink is due to the fact that the scaling of the error is different in both cases. So in the Taylor case, the error scales like I don't know, t, right? I think it's first order. It should be first order, I think of it. But in the second case, it scales like t to the power alpha. And this alpha depends on the circuit depth, right? So the slope of this yellow curve, it increases as the circuit depth increases. And that's actually a good thing, because that's the order of the Trotter formula. Basically, the slope that we see here corresponds to the order of the Trotter formula. Yeah.
Okay, that makes perfect sense. The next question I would have on this is if we compare the different optimizers that we have, or the Trotterized circuits to these different ones. There's a region here in the beginning where there's a region here, let's say, where the classically optimized circuits outperform in terms of error the Trotterized ones, and then there's a region here where the opposite is the case. Do you have a reason or an explanation for why this early region, why we underperform in the early region with the classically optimized circuits?
It's a Taylor error. It's just that it's because we're using a first order Taylor approximation during the optimization. If we were to use the Trotter formulas, right, that are shown here, like there's different ways one can do the optimization, this iterative quantum circuit optimization. So we chose to use a Taylor approach for several reasons, but we could have used a Trotter formula like the ones that are shown here, in which case these blue lines should have been lower, right?
Okay, no, that's clear. Maybe then we can look quickly at the other figures that you have as well. So maybe if we move over to figure 3 here, would you mind explaining what we see here, like what this graph is meant to represent?
So this is basically the main result, which shows so there's a lot of data in this figure, right? So first of all, it's important to emphasize we're showing the same error as before. So it's an error that tells us about the accuracy of these classically optimized circuits compared with exact circuits, right? With the exact Hamiltonian simulation. So we're still looking at small systems where we can calculate the exact Hamiltonian simulation, and we are comparing the classically optimized circuits to the exact case. And we do this for system sizes 5, 8, and 10. So this is the dots, the dashed and the solid lines, and we consider circuit depths 1, 2, 3, 4, 5, 6. So what we're trying to see here is what happens. So how does this error that we get from our classical circuits change with system size? Right. So there's a dependence on n that we can see, and how does it change with circuit depth? And what you see is that so if you fix the circuit depth, let's say we look at the first set of 3 lines. Then with system size going from 5 to 10 qubits, the error grows slightly, right? So it increases. So that's one observation, and the other observation is that as you increase the circuit depth, so as you go to the right, the error simply gets lower, right? And at the same time, the slope gets increases, and that is so there's a table there, Nicholas, where we summarize the slopes of these curves and the prefactors, and it's really the slope which tells us the exponent of t, right? T to the power alpha. That gives us this big advantage over Trotter. So if you compare Trotter here, so the situation here is that we assume the same circuit depths, right, for the Trotter circuits as for the classically optimized ones, and then we compare what kind of errors do we get from Trotter for the same circuit depths for these system sizes 5, 8, and 10. Compared to the classically optimized circuits, and one can compare these by fitting a function to this error, and that function it's known for Trotter for these type of problems that there's a prefactor c of n that depends on the number of particles, system size n, and it's times t to the power alpha. So Trotter formulas have this error scaling for this type of problems. And we see the same error scaling for these classically optimized circuits, with the key advantage that this prefactor C is orders of magnitude smaller than in the Trotter case, and the exponent is larger than in the Trotter case. So that's really, this table is really that summarizes this advantage. Yeah.
Okay, very good. I just have one follow-up question if we go to the table here again. So we said that if we compare 2 different ones, let's say different number of layers in them. So we compare this one here to the deepest one, and we're saying that the error decreases as we increase the number of layers. Isn't that so? What do we mean when we say that? Are we evaluating this on a physical machine, and we're evaluating the error, so that we're also taking into account the noise of additional layers in our circuit? Or what are we actually taking into account? Because my understanding is when we increase the number of layers, we're also increasing the depth of the circuit that we're evaluating. And my sort of gut reaction would have been that if we're increasing the depth of the circuit, we would incur more noise from the gates. But that doesn't seem to be reflected in the figure. Am I thinking about that in the wrong way?
No, you're absolutely right. So the noise is not included in this analysis here. So this figure doesn't contain realistic noise. It doesn't contain any noise. So this figure is just about a perfect quantum computer without any noise. Yeah, how would that behave? But so if you add noise, the situation changes, and you will have you will have a so you should have an optimal because what happens with noise is sorry is that it simply increases your error, right, as your circuit gets deeper. So now you have these two competing effects happening. So one effect being your Hamiltonian simulation error, right? This algorithmic error decreases as you increase the circuit depth. In the absence of noise, right? That's exactly what happens. You increase your circuit depth, your Hamiltonian simulation error goes down, right, for fixed time.
Mm-hmm.
But at the same time, now your noise builds up, right? So you have this this other error that actually grows now as you increase your circuit depth. So you can imagine that there's a sweet spot, and you can actually find that sweet spot. So depending on your noise rate, you can. So we do a very preliminary analysis of noise in that paper. There's something, I think in an appendix or maybe in a discussion. It's briefly mentioned.
Yeah.
But it's an important point. Yeah. But it's not really the focus of the paper, the noise. Yeah.
Mm-hmm. Yeah. In the interest of time, so I won't go over to the appendix. We'll link the paper in the description anyway. So if someone's interested, they can have a look at the appendix. But just sort of hand waving here a little bit. Do you have a conceptual feeling for if we were to introduce noise in this graph, how it would change? So naturally, the deeper ones would get more noise, but would that, with the current, let's say, technology that we have and the significant noise associated with the circuits now, would we see a change in this graph in the other direction, so that the deeper we get across the board, like does the noise from additional layers dominate the benefit that we see in this graph? That's basically my question.
So the noise of the additional layers will have a very serious effect. So Niklas, do you think you could just go to the discussion section? We have a figure that assumes different levels of noise, and so here you can see the so here is it's a very simplified discussion of noise, but it points out the challenges that you're mentioning. So basically, what happens is if you fix the circuit depth, the noise level is constant. So now if you have a fixed circuit depth, you can compare trotter at that circuit depth to the classically optimized circuits, because they have the same noise level, right? They will suffer similarly or in the same way from that noise, right? Mm-hmm. So now you can go and follow these green lines, right? So these green lines correspond to different noise levels. So 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. So in this figure 1...
A quick follow-up a quick follow-up question, if I can jump in here before we go further. Right. Is it really fair to do a comparison between the same circuit depth for these two? Because the entire point of the classically optimized circuit, as far as I understood it, is to compress the trotterized version into a shallower version of a circuit. But then it seems like we're nevertheless going back and saying, for the comparison, we're considering these to have equal depth. Would it not be like, is not the fair comparison, quote unquote, to make to compare the same the same conceptual task on whichever circuit depth they actually end up in after their subsequent optimization procedures?
It's a very, very good question, Niklas. I think what you're proposing makes sense too. So our motivation was to look at it from the hardware side. So to look at it from the quantum computing perspective, where gate errors are significant, and we can only work with a certain depth, right? So because gate errors are significant and there's no quantum error correction available yet, we are basically limited to a certain circuit depth, you know? So what we care about is if we have a certain circuit depth, let's say 10 layers, right? What can we achieve with that? So now we can put trotter into these 10 layers, or we can put these classically optimized circuits into these 10 layers. But what we compare here is really fixed circuit depths, right? So it's an experimental motivation.
Okay, fair point. I'm sort of, well, this was an excursion, and I want to bring you back on track because we need to run off very soon. So I would jump to unless there's any additional figure that you really want to show. I would jump to the conclusion section, and we could just wrap up with the main findings of the paper and like what the next steps for your research would be.
Yeah. So, so I think that what we've seen in this project is really that it's worthwhile to optimize circuits classically for Hamiltonian simulation. That we can reduce errors for the same time, right? For the same considered Hamiltonian simulation time by orders of magnitude over Trotter product formulas. Yeah, that's certainly what we've seen there. Yeah.
Mm-hmm. And then looking forward as well, is there anything you would like to follow that up with? Like, are there future directions for the research that you think would be interesting to pursue, or something like that?
So one thing that we've done is since then we've applied these techniques to adiabatic quantum computing. So so I'm working for a quantum computing company, right? Quantinuum, and so one thing we're doing there is of course running these circuits on our device, and Hamiltonian simulation is a wonderful application because it's very much believed to be classically hard. So we look into these things and we keep exploring them to run them on our device because they're classically hard, these kind of circuits. But another topic that we're looking into is adiabatic quantum computing, which has many more, perhaps more applied applications, like finding ground states, right, or solving combinatorial optimization problems. So in that context, similar techniques can be used, and similar advantages can be achieved compared with Trotter formulas.
Very good. Okay. Is there anything else you think ought to be raised before we close the discussion? Anything else you want to say before we wrap up?
Yeah, I think what I should have said at the beginning is that the main person here who did most of the work is Connor McKeever. So one of my colleagues, he deserves all the credit, actually, yeah, for this paper, and I think he's done a great job here, yeah.
Okay, very good. With that, then, I would thank you very much for taking the time.
Thanks a lot, Niklas, yeah.